Warm up, we solved, some of us by substitution, some of us by elimination. You can choose different variables, etc., and solve for either one. But no matter what you get, no matter what you choose to like solve by elimination substitution, you should get infinitely many solutions right off the bat. Okay. Now, we had this conversation last Thursday. Infinitely many solutions is a different answer than all real numbers. Never should you ever write all real numbers, right, in this particular instance. Okay. We're saying that there are infinitely many solutions. In this case, these are two lines on a two-dimensional plane. So what do you know about the two lines? In order for them to cross at infinitely many places, they must actually be the same line, right? So that they're sitting on top of each other and crossing at all points. Okay. And so it's really only the points on that line that actually work. It's not like all the points on the plane that work. So this is what you're going to see that's different in pre-calculus, different in Chapter 7 that you want to make sure you master and you're practicing on your homework tonight. Okay. When you get to answers like infinitely many solutions, I want to know, what do all of the x, y ordered pairs in that infinitely many solutions look like? Okay, so like it's not like I can just put in any x and any y and it'll work in both equations. There's a certain line that has the correct x's and y's. Okay, so here's what we're going to add to our work today when we get to infinitely many solutions. We're going to let one of our variables, one of our unknowns, equal something. And instead of like giving it a number, because then we would just get one solution, we're going to put in a placeholder. We're going to call it A. So it's going to feel weird. You're going to either let x equal A or let y equal A. Does it matter which one you choose? Nope, it does not. I will tell you this. I think looking in the textbook at my answer key and like looking at the back of the book generally takes the later variable like z or y and sets it equal to A. So I just do like the back of the book does in hopes that like if I'm checking my answer it would look the same. Okay, but if you let x equal A, that would be fine. Okay, so if y equals A, some number, then in my ordered pair, xy, the y is A. Okay, and maybe A is 0, or maybe A is 1, or maybe A is negative 250. Don't know. Don't care. If y is A, what's x? Okay, that's the question that we're asking ourselves. If we let y equal A, then what will our x be? Well, if we knew that y was 5, how would we find x? Plug it into an equation and solve. Okay, so we can choose either equation. It doesn't matter. Row 1, row 2. I'll just choose row 1, and we can sub in A for y. So let's do 3x minus 12a equals 6. Do you see where I'm doing that? I'm substituting a in for y because I let y equal a. Okay. What thing do you want to find in the ordered pair? X. So you want to solve for x. This is where it gets tricky. Sometimes people start solving for a's. You want to solve for the variable you want to put in your ordered pair. So how would you get the x all by itself? Add 12a to the other side, so we have 3x equals 6 plus 12a. And divide by 3. And so whenever y is a, x is 2 plus 4a. So now when we say infinitely many solutions, we can actually give a set of ordered pairs in terms of A, where like these would generate all the possible solutions that would work. Okay, now what I'm going to want to see in your answers is that ordered pair, 2 plus 4a, comma A. And if you let x equal a, you would have a different ordered pair, but it would still be right. Okay, you would sub a in for x, and you would solve for y. Okay. But what this means is, if I generate a table of values, okay, in order to get my x's and my y's, I actually need an a, right? So I'm going to add, I'm going to create like a 3 table. I'm going to add an a over here. Okay. If a is 0, then y is 0. And 2 plus 4 times 0 is 2. So 2, 0 should be a point that works. If 2, 0 was a point that worked, that would mean if I plug it into both equations, it makes both equations true. So I'm going to check over on the sideboard here. 3 times 2 minus 12 times 0, that should equal 6. Well, that's 6 minus 0 equals 6, that checks. And if I plug it into the second equation, it should also work. 2 times 2 minus 8 times 0 is equal to 4. That's 4 minus 0, which is equal to 4, so that also checks. But that's not the only solution, right? There's infinitely many solutions. So I could pick a new value for a. What do you want to let a equal? 4? Okay, let's let a equal 4. If a was 4, then y is 4. And x is 2 plus 16, which is 18. Okay, so now if I take 18 and 4 and plug it into these equations, it should also work. So I'm going to put 3 times 18 minus 12 times 4. And 2 times 18 minus 8 times 4. Okay, well 3 times 18, that's 54. And then minus 48. Is that equal to 6? Yep, that works. 2 times 18 is 36 minus 32. Is that equal to 4? Yep, that works. So all that's saying is you could choose infinitely many a's, and you could generate the list of x and y's, and these will be points that lie on the line. But I would never say what are the actual solutions, because there's infinitely many of them. So you just write them as the ordered pair. 4 plus 2a, or sorry, 2 plus 4a.
Why are we just able to say that y equals a?
Well, because you could let y equal 5, right? And then you would solve for x. If you knew y was 5, there's infinitely many solutions. At some point on a line, y is equal to 5. Then what's the x value? And you could solve backwards for that. But because you're actually letting it equal a number, then you're only finding one x. And you would have to find what if it's 5.1, or 5.01, or 5.001, and 6, and negative 5. And you can't list all those solutions. We don't have that kind of time, right? Infinitely many means not countable. So we're just saying let y equal a number a. But we don't actually know what that a is. If we want to generate some points, we can pick a's. But all the points will have this relation. So you as a mathematician are just saying, let y be a number. We're not going to call it y anymore, so we're going to call it a. And then you're showing all the solutions. Okay? All right, let's take our notes for 7.3. If you look at the gold sheet for Chapter 7, it does kind of jump around in Chapter 7. That green sheet is titled 7.1 and 7.2 Practice. So I'm not going to reteach you how to solve two-variable systems, because you've been doing that since Algebra 1. And you want to make sure that you've taken the time to go through that green sheet and you feel confident in your solving skills. If you're feeling I don't remember substitution and elimination, set aside some time to come in and see me. Okay, so this first example is one like number 7 and 8. Do you want to work through a 3-variable system together? Okay, so I'll walk you through how I think about solving a 3-variable system. And we're going to see more 3-variable systems, but we're going to see that like piece that I just went over in the warm-up in the other examples. Okay, so if you want to write down these equations, I'll read them, and you can kind of double check that you wrote them down correctly. We've got 2x plus 4y plus z equals 1. We have x minus 2y minus 3z equals 2. And then x plus y minus z equals -1. Okay, and like, it does not matter to me what kind of naming system you're using here. I'm going to go ahead and call them row 1, row 2, row 3. And the reason why I like to call them row 1, row 2, row 3 is in our next chapter with matrices, we're going to call them rows. So we're kind of like prepping ourselves for chapter 8 already. Okay, when you have 3 variables, that's too much going on. So basically what we want to do is create a 2-variable system. Okay, if I have a 2-variable system, then I would have 2 equations in 2 variables. Now I'll be able to solve like the front side of my green sheet. So you can look over the 3 equations and decide like what variable might you like to get rid of, might be easy to get rid of, right? Because we have 3 now, we only want to have 2. So what's a variable you guys want to eliminate? Y. Why did you choose Y? How would you eliminate Y in row 1 and row 2? Multiply by 2. So the X's wouldn't eliminate. Yeah, but that would be awesome if they did. Okay, could you eliminate Y pretty easily? Yeah, does anybody want to make an argument for a different variable? X, why would you choose X?
So you can multiply row 1 by -1. No, row 2.
Okay, row 2 by -1 and row 3 would be positive X then, and then they would cancel. Yeah, you're not going to do all 3 at once. You're just going to pick 2 equations at a time.
Can we just do row 1 and row 3 and cancel out Z?
Oh, hey, isn't that nice? All of those are right answers. On this one, I'd say X, Y, or Z is fine. But I would, if I looked very carefully, I'd choose these. Because then I can start with row 1 and row 3. And I don't have to do anything to them. I just copy them down. So I have less room for error. Stack and add is what we're doing in elimination. So I get 3x plus 5y. Of course, my z's canceled out, and that equals what, 0? So I call that, like, that's a new equation. Someone call it row 4. And that's 3x plus 5y equals 0. Okay. Well, I've created a 2-variable system in that I have 1 equation in 2 variables, but really to be able to solve that, I need 2 equations in 2 variables. So we eliminated z in row 1 and 3. Now we would like to eliminate z in row 2 and row 1 might be nice. Okay. So row 2 and row 1. Row 2, just leave it as is. X minus 2y minus 3z equals 2. But what are we going to have to do to row 1? To make z's cancel, multiply by a 3. 6x plus 12y plus 3z equals 3. Okay, so that when I stack and add these, I get 7x plus 10y, of course my z's canceled, equals 5. And that's my row 5. Okay, so I'm going to go back up here where I said eliminate Z, and I'm going to add a very important word. Eliminate Z twice. Okay, sometimes when we aren't really thinking about our process, we might like eliminate Z, and then like Katie said, X's would be really easy to eliminate. We might eliminate X's next. But by doing that, you create 2 equations in 2 different variables. One in Y's and Z's, and one in X's and Y's. And you have to have a 2-variable system that has the same 2 variables. So you want to eliminate the same variable 2 times. That way you get a 2-variable system in X and Y. Okay, can you solve that 2-variable system for me? Whether you choose substitution or elimination is your choice, but I would probably choose elimination. You need to eliminate either the x's, 3x and 7x, or the y's, 5y and 10y. Which one would be easier? The 5y and the 10y, you got to multiply the 5y by, then they'll be the same. That would be 20y when you add the -2. So you're going to multiply row 4 by -2. Okay, so you choose, Lexi, what to multiply by.
Does that mean also multiply the 0 by -2?
Yep. Okay, I'm choosing to eliminate the y's, so I get x equals 5. Plug in that 5, so 3 times 5 plus 5y equals 0. That's 5y equals -15, so y equals -3. And then to get my z in the end, I have to go back and use one of my original equations, so 1, 2, or 3. So I'm going to plug into row 1. So I have 2 times 5 plus 4 times -3 plus z equals 1. So that's 10 minus 12 plus z equals 1. And what do we get? Z equals 3. Okay. But you know, like that little chunk right there, solve the 2-variable system. Like we should be able to solve the 2-variable system by substitution or elimination, right? That should be a skill that we all have. And if you're feeling like you don't, then you should come in and ask. Okay. But once you get those 2 answers, then you just have to plug them into one of your other equations, and you'll be able to solve for the missing variable z. Okay, what's your ordered triple then? 5. -3, 3. How do you know where the numbers go? They go X, Y, Z in alphabetical order. Okay, so if you didn't do 7 and 8, you need to take some time to do that 3-variable system. I know everybody has got here by solving a 3-variable system, so we just need to like tune our skills. Okay. Now I'm going to do another example. This one will go just a little bit faster at the beginning, because as you're writing down row 1, x plus 2z equals 5, it's already missing a y, right? So that's good, right? We already, like if I'm thinking about my 2-variable system, we already have one equation. So row 1 is x plus 2z equals 5. Row 2 is 3x minus y minus z equals 1. And row 3 is 6x minus y plus 5z equals 16. Okay, in my 2-variable system, I can already put in row 1. which that tells me if I want to use that equation that has only two variables in row 2 and row 3, I'll need to eliminate which variable? I have to eliminate the y if I want to use that row 1. Okay. So I'm going to eliminate y in row 2 and row 3. Tell your group right now how you're going to eliminate y's. What are you going to do to eliminate the y? Speak to your group members.
I multiplied row 2 by
What are you going to do to eliminate the y? Tell your group members. What do you guys say? Which one? Okay, so pick a plan.
Oh, it really wasn't that bad.
It was bad in the States. Everyone had a blink on. There was a lot of people. I could not feel my toes by the end of the night.
Okay, Mike, which row did you guys decide to change? Okay, so you multiplied it by -1, row 3?
Yep.
So we get -6x plus y minus 5z equals -16. You'll remember as you do these, like back to when you did them in Algebra 2, where if you make a tiny multiplication or sign error, that ruins your whole problem, right? So you just have to be really careful, really deliberate. That's why like labeling your work can be super helpful. Add down, I'm going to get -3x. My y's will cancel, minus 6z equals -15. That's going to be row 4, which I can add to my two variable system. -3x minus 6z equals -15. Okay. And if your group chose to multiply row 2 by -1, you should be okay. You have a different equation. It'll just be flipped signs, but you'll be fine. Okay, now how are we going to solve our two variable system? Elimination. Just multiply row 1 by 3. So 3 times row 1 is 3x plus 6z equals 15. And row 4 is -3x minus 6z equals -15. Oh no, what's happening? 0 equals, should be 0. Did you forget to multiply 5 by 3? Oh, did you get 0 equals 0?
I did. I multiplied row 2 by
Yeah. So then it should have been 3x plus, it would have been 3x plus
plus
6z equals positive 15. Okay, but did you still get 0 equals 0? You should, okay. And this means what? Infinitely many solutions, but we're in pre-calc now. So we don't have to stop there. We can tell everybody what their ordered triple is going to look like in terms of some number A. Okay? Now, look at your two variable system. What two variables do you have? Two variable system.
X and Z.
X and Z. You can choose. Do you want to let X equal A? Do you want to let Z equal A? Let's let Z equal A. Now, you could do let X equal A, but I'll say this. If I'm thinking ahead in the problem, because if I let Z equal A, what's really easy to solve for now? X. There's just a 1x. All I have to do is sub A in and then move that to the other side. Bam, I got my X value. If I put A in for X, then I still have to divide by 2. Okay. So we're going to let Z equal A. That means the last value is A. And we're going to say X plus 2A equals 5. Therefore, X equals 5 minus 2A. Remember, don't solve for A, solve for X, Y, or Z. And then how will you find Y?
Plug the holes in
plug those two values into row 2 or row 3. It should not matter which one you solve. If you've done your solving correctly to this point, it doesn't matter which one you use. I'm going to copy row 2. 3x minus y minus z equals 1. So down here I'm going to copy that. Row 2. 3x minus y minus z equals 1. Did I copy row 2 correctly? Can you double check? Okay. So now let me plug in. 3 times 5 minus 2a minus y, which I don't know, minus z, which is a, equals 1. Distribute that 3. That's 15 minus 6a minus y minus a equals 1. And again, just stop yourself. What are you solving for? Y. You want the numbers that go into the order of triple, x, y, z. So we're trying to find that y spot. So now we want to get y all by itself. I'm going to add the y to the other side if you're okay with this. So this is 15 minus 7a equals y plus 1. And then subtract my 1. So y equals 14 minus 7a. If you had let x equal a, you would have some fractions over on the other side, which is totally fine. It isn't wrong. I'll give you full credit for that if you let x equal a, as long as you solve for the y and z fractions. But there is like only one answer that you can have when you let that variable equal a. Okay? Just as a side note, if I asked you to give like one example or one solution, okay, if you just wanted to know like what is one solution that works, you would just think about a, x, y, and z, and you could let a be anything. What's always a nice thing to let a equal? 0. That's pretty easy, right? Because then y is 0, and x is 5, and y is 14. So 5, 14, 0 is one solution that works. One of infinitely many. If I take 5, 14, and 0 up to the top 3 equations, 5 plus 2 times 0 is 5. It works. 3 times 5 is 15 minus 14 is 1 minus 0 is 1. It works. 6 times 5 is 30 minus 14 is 16 minus 0 is 16. It works. So I plug that value in and it works for all. Okay, questions, concerns? Imagine the amount of points you could lose if all you write is infinitely many solutions. Because you haven't done any of your practice in chapter 7. And you don't know about let z equal a. That would be a bummer. So please make sure that you've done your practice so that you can get all of the answers. Okay, last thing that we need to talk about is something called a non-square system. Sorry, Nikki. It'll go faster this time. When we talk about non-square systems, it basically means this. The number of equations does not match the number of variables. So I've said it before, like if you're solving a 2-variable system, then you need 2 equations. Otherwise, you can't solve for your unknown. If you are solving a 3-variable system, then you have to have 3 equations. Or you can't really solve for your variable. Now that we know about this piece where we can come up with this like list of points that would potentially work if we just could pin down our a value, we can find the infinitely many solutions here and write them out as an ordered pair. So like if I were doing this problem, I would call this row 1 and row 2. I can eliminate any variable I want. I might choose to eliminate x. Multiply row 1 by -5 and keep row 2 the same. then of course my x's are going to eliminate. I'm going to get 2y plus 2z equals negative 10. And that would be like my row 3 now. But I'm out of equations to eliminate y. Or x. Sorry, I eliminated x. I'm out of equations. I already eliminated x in equation 1 and 2. And eliminating x again there is just going to give me the same result. So I don't really know what y and z are. But we're going to play that same game. Let one of them equal a. Which one do you want to let equal a? Z. It does not matter. You are fine to let y equal a. Letting z equal a is good practice for your homework because I think the book lets z equal a most of the time. Of course, if you eliminate z, then you have to choose x or y. Okay, so then in my ordered triple, z is a. I'll say 2y plus 2a equals negative 10. 2y equals negative 2a minus 10. Therefore, y equals negative a minus 5. Or negative 5 minus a. Doesn't matter which way you write it. It's all the same. And then to find x, use one of the first equations. So I'm going to use probably row 1. Will you guys read row 1 to me? X minus 3y plus 2z equals 18. Okay, so I can say x minus 3 times negative a minus 5 plus 2 times a equals 18. And I'm just cleaning that up so I can solve for x. So what do I get? X plus 3a plus 15 plus 2a equals 18. So that's going to be x plus 5a plus 15 equals 18. So x is negative 5a plus 3. Squeeze that in a little better. I think in my second hour we let y equal a, so we had different answers than for x and z, obviously, right? So it doesn't matter on the quiz or the tests. I will have worked out, like if I let x equal a or if I let z equal a, and if I don't work that out, then I can work it out like on the side and make sure that you have the correct answer. So either way is fine. It doesn't matter what you choose. There are occasions where like one way, like we said in the last one, is easier than another because you might introduce fractions. And if you just want to avoid fractions, try looking at it like what would be an easy one to solve for. Okay. So your homework assignment are these 7 problems. I think 497 is going to be 3 variable. And I think 474 and 484 are going to be 2 variable linear or nonlinears. So again, Chapter 7, really important. You have to be doing this work. There's a lot of algebraic solving. You will not know if you can algebraically solve something unless you try. And I definitely won't know unless I see you trying. So please find the time. Do 7 problems. That seems reasonable to me. Okay, if you work in tight time, you probably get it finished.